My guest today is George Woolridge.
My education is kind of interesting because even though I grew up very interested in the sciences, I started out as a computer science major. I actually switched to music education. So my qualifications are K through 12 education. But I actually spent the last 20 years working in electronic design for a couple of companies. So I'd like to start with a lot of scientists. If you look up the history of a lot of scientists or philosophers throughout the years, you'll find out that most scientists dabble in philosophy, most philosophers dabble in science. There's a huge crossover, partly because to come up with new ideas, it seems like you have to be able to think outside of the box, whatever your box happens to be. So over the years, I've kind of settled on a personal razor that I use to judge pretty much every theory, every idea that I come across. Philosophy, theology, science, it doesn't matter what it is. So I wrote it here. I say, for something to be true, it must be true in all places and at all scales. And what inspired me particularly to think that way is I find that a lot of scientists focus on a specific problem, a specific something in particular that they want to get the answer for. And once they find something that looks like the answer, then they think they figured it all out. They're done. But you can't take that theory into another field, or you can't apply it to another dynamic and have it work. It doesn't always work. I mean, a good example is Newton figured out how planets and gravity works, but Einstein found where it doesn't and enhanced it. And as we continue our different research and studies in astronomy, we find lots of gaps in how even Einstein's theories apply. So to me, how I judge science and philosophy and theology is if something's true, it should be true no matter what, and anywhere and everywhere. And if you find a situation that it doesn't fit, it's probably that your idea, your philosophy doesn't fit everything. You need to work on that, not come up with a new special philosophy at the periphery. So I have a couple of I'd like to call them my power animals in this kind of thinking. Lots of people talk about Occam's razor, William Occam, the idea that you want to have the whatever has the least number of parts answers the problem best. Technically, he said entities are not to be multiplied without necessity. So the idea of taking what exists and seeing if that fits everything is something I call it the reduce, reuse, recycle principle, which I find is rare in science. Scientists want to come up with a new idea, something new and shiny, not necessarily see if what exists fits all spaces. But then on the flip side, to balance this out would be Rene Descartes, who this isn't technically a razor, but he has the idea, I think, therefore I am, or he also says, I doubt, therefore I am. The idea that, honestly, do you know why you exist, Tom? Do you know that you exist? That's the only thing you can be sure of, is what he said, is I know I'm here. I can't answer why, but there are some fundamental assumptions that until we figure out why those assumptions are true, you might just have to start with a few assumptions, but as limited as possible. You don't assume everything that you know. You can only assume what you can't prove otherwise. So those two guys, I think, kind of balance out a good way of approaching science, and you'll find lots of people quote them. I'm concerned whether or not lots of people apply them. Yeah. So to kind of take that into environmental concerns, and if it sounds strange that as a kid I would think this way, I guess that's just me. But I like to try to. I've always considered environmentalism efficiency. If you waste less energy, then you've been more efficient. If you use less resources, you've been more efficient. And efficiency is how you utilize less of the earth, how you're efficient with the earth. So I kind of, for this discussion, threw together a little equation where I call it ethical Newtonian inspired stewardship, because I'm looking at energy output and having the ethics of how do you minimize impact through looking at it mathematically. So when you produce something, you have your impositions, which is either your taxes or the cost of production, whatever it is that takes away your end result. Then you divide it by the amount of work and time you want to put into it, and that's your standard of living. If you make so much money doing so much work and then have so much time to play or can buy the house or whatnot that you want, that's your standard of living. And that's individual. Everyone has a different one. And I'd say for most people, we just want to be, including myself, we just want to hit a level of comfort, and we want to be happy with what we've accomplished, without going so far as to burn ourselves out, or undercut our possibilities as we want to. So for the most part, taxes, regulations, they impositions of all kinds typically will lower efficiency. Even like the cost of materials will lower your efficiency, or the taxes will lower efficiency. But there's a gray area for all of it. So if you've ever heard of the Laffer curve, that's the economical theory that if you tax your society too much, you actually collect less money, because they'll either accept a lower standard of living, or you'll inhibit production to the point where you don't even benefit from it. And that's an argument for moderating taxes. Even people that are environmentalists, overtaxing a society or overspending on projects that one would think would benefit the environment, are counterproductive in many cases, because they make people either accept a lower standard of living, or they don't care about the environment, or you end up collecting less money for those programs to begin with. It's an irony, and a few people in environmental studies seem to care about the economic flow that would support their programs anyhow. So I think excessive impositions, which, I mean, some of your guests have even said that might be the point. Maybe the point is to accept most people to accept a lower standard of living for one reason or another. But then on the flip side, Richard Nixon started the EPA because there was so much environmental damage being caused by some forms of production, that those impositions and those regulations actually improve the standard of living. Or in the case of taxes that go into a road system or something, does help improve the flow of traffic, does help the flow of commerce. So impositions can be reinvested into standard of living. So you never really want to be black and white on any issue. You do, like an equation like the one I have shown there, you're trying to find the balance that gives you the result that you're looking for. And yes, this is kind of how I usually think. and I assume that many people feel this way or think this way, even if they don't put it into numbers or terms. So just a quick conclusion on this. I think there is the responsibility for all collections, for all impositions, to be efficiently and effectively used. If it isn't objectively showing a benefit to standard of living, or it isn't improving any of the other variables, it is mathematically incorrect. So I would like to broadly say that, as I've been following it, and as your podcast clearly shows, I believe that environmental issues that have been government supported since the 1990s, have all been just across the board been incorrect and pointless. I would just throw them all into the same basket and say that they've all been wrong, because so many of them have either disproportionate impositions to the point where you can't have $1 trillion program without producing an extra $1 trillion, which how do you do that without producing more output and more emissions, or convincing companies to go offshore where there's less regulations? So then you've moved your problem. Almost every Western country has done this. Even in Europe, you'll have England produces less power, so then they move it off to to Germany or Spain, and then they produce extra power with lower regulations. It doesn't really help. And then more recently than not, the odd interest in replacing green in farm space has been bizarre. I thought green space was the point. So what's the mathematical reason to remove your green space with something that's supposedly green but not? So my argument for why my periphery interests and all interests are frankly green and environment related, no matter what your opinion, no matter who you are, is mismanagement of funds or programs that have disproportionate impositions for any reason are bad for the environment mathematically. So that's my thoughts on that. Getting on to my personal interests, I have a couple of thoughts. I consider it my midlife crisis that many of the questions that I've had over the years, I have been over the last decade actively searching for an answer to, and being heavily involved in the industry I am. But lots of the customers I have are research labs, are government facilities. Lots of the people I discuss things with are highly technical discussions. So I find that I'm mentally in the space of wanting to reason, wanting to rationalize technical items. That's kind of what I do most of my day. But for myself personally, I find lots of questions in history, philosophy, and science that I've been hoping to find answers to that I haven't felt were adequately addressed. So I've recently been over about the last decade. I've worked on trying to find solutions to certain cosmic observation theories that I never found adequately answered. Even though we've had answers that fit some solutions, they never fit all solutions. And you read articles about exceptions to these theories more than you find cohesiveness, agreement between different theories in different spaces. So to get into it, I'd like to give what I call a brief and selective history of gravity. Over 500 years ago, or about 400 so years ago, Johannes Kepler was an astronomer who identified he characterized the orbits of the planets. But what made his characterization interesting is it was so detailed. He discovered that no planet, no object has a circular orbit. There is no planet going in a perfect circle around a point, any point in space. There's always a ellipse to the orbit. And he had the detail to characterize the difference in speed of the planets at their different points in their orbits as well. Isaac Newton, who I would probably vote for as maybe the smartest guy to ever live, took that information and was able to calculate what we have as the law of universal gravitation through the equation here. He from just the observations of Kepler, he designed the equation which we accurately used, even till today, we accurately use to plot the orbits of the planets to predict where they're going to be. And through math alone, and through the orbits of the planets alone, we discovered Neptune. Not because anyone could see it, but because the orbits of the other planets suggested it was there. So that's how effective Isaac Newton's equations were based on Kepler's observations. So jumping ahead to Albert Einstein, now he found an exception, there was an exception to Newton's equation and Kepler's observations, and that was the planet Mercury. And the issue with Mercury, it's so close to the sun, no one had been able to observe it until after both Newton and Kepler had passed. But when they did observe it, and when they did try to characterize the orbit, they found that, again, it was very odd, kind of like how Uranus's orbit was odd, and they found Neptune. Mercury's orbit was odd. And I'm not sure if you've ever heard the old stories about the planet Vulcan that allegedly would exist on the other side of the sun. It was a very, very brief period that people believe that. A couple of articles popped up over 100 years ago, but there was really no way they could support it. They only knew that there was something wrong with the orbit. It didn't move the way they expected. So Einstein was recognized as the first one to the finish line with an explanation for Mercury's odd orbit, and that is essentially time dilation. So his equation of general relativity, he characterized that there's appeared to be a difference in rate of speed, maximum rate of speed of particles or matter, if there was a large presence of gravity. Now that presence has to be strong enough to make a difference that you could notice. So the small planet Mercury near the large object of the sun made enough of a gravitational curvature in space, as some people would say, to make the orbit noticeably incorrect per Newton's math. So he characterized it, and a quick side note for anyone that for anyone that doesn't know this, Albert Einstein said that gravity is actually fictional. It is not a direct force. Time dilation is the real effect that we observe through gravitational effect. So it's a little bit backwards than many people believe, but that is specifically what he characterized. So it is kind of a flip-flop to what people believed before Einstein, and actually it's still kind of a flip-flop to what most people seem to believe today. But them's the facts. Now, moving over to a contemporary of his is Edwin Hubble. And it seems odd to think this, but before Edwin Hubble made his observations in the 1920s, we collectively, everyone on Earth, only believed that there was one galaxy. The entire universe was the Milky Way galaxy. So we had a reasonably good idea of the size of the Milky Way and the stars contained therein, but we thought that was it. That was the whole universe. He discovered that some stars that had interesting characteristics were not stars at all. They, in fact, were themselves other galaxies at vast distances away that we didn't even know were possible. And also through those observations, he created Hubble's law that the more red shaded or the more shifted that the color was, equated how far away it was. So redshift basically is just it's the Doppler effect of light. So where you think where sound is shifted down because an object is moving away, like a train passing by. The same thing happens to light because it's a wave and it has frequency. So between the two of them, they have a couple of ideas that are interesting. On the left side with Einstein, even though he characterized gravity as time dilation, but his equations also showed that gravity, or the effect of gravity, would seem to have a speed of motion and could have waves. Oddly enough, he thought that those waves would be irrelevant or even considered math error. So he didn't think gravitational waves were relevant at all. The second item is that his conceptual belief of the universe, as was most people at this time, is that the universe had existed for forever, that the universe was static and didn't change fundamentally, and was eternal, no beginning, no end. But the third item I want to mention is something called the cosmological constant. Because he believed the universe was static, but he understood that stars would collapse and planets would be drawn together and objects eventually would through friction or one way or another would eventually be pushed together. This bothered him because he wanted the universe to last forever. So he had this idea of having a cosmological constant, something that was a pressure that would push everything away from each other. But he couldn't necessarily define it. He had contemporaries that would argue with him that it wasn't necessary for one reason or another. But he wanted to make sure the universe stayed the same. Well, with Edwin Hubble, people believe that he meant with Redshift, he also came up with the idea that the reason why there's Redshift is because everything is moving away, the expansion of space. So he kind of formalized the idea that the fabric of space or the medium of space is being stretched over time, so that everything looks like it's moving away, and the further away it is, the faster away it's moving. So he proposed that idea. But oddly enough, he also believed that the universe was static and lasted forever. So I'm not even sure exactly how to resolve those thoughts, but from what I understand and what I've read, those were his beliefs throughout the rest of his life, trying to resolve an eternal universe with one that appears to have acceleration or expansion. But at the end of it, Einstein was happy to hear that there was some outward expansion idea, and decided that was a better idea than a cosmological constant. So moving on to a few other rock stars, the pair Penzias and Wilson discovered and characterized the cosmological microwave background. Now, what makes this interesting is it's a noise that is everywhere. You can detect it everywhere in the universe. Allegedly, it's why you get a snow white screen, or like those that snowy screen on an old TV, is because of the cosmic microwave background. It actually causes some of that FM interference. And but having had observed it, it implies that the universe had a beginning because it's an even signal that's in all directions, and with a very similar characteristic. So we use that as evidence that the universe had to have had a beginning, and that all the matter in the universe, on a grand scale, is evenly distributed, which makes for some interesting philosophical points as well as issues in science that need to be addressed. Skipping over to another topic, Richard Feynman was a scientist, is a theoretical mathematician who disagreed with Einstein's earlier comments regarding gravitational waves or gravitational radiation not having any energy. He believed that it had to be energetic, and even came up with some tests that one could use to prove that there's energy to gravitational waves. And so if you're familiar with the LIGO experiment, I'll end up referring to it again, but the LIGO experiment is the one that detected gravity waves from colliding neutron stars in 2017, as well as other observations. So it was the big science news of 2017. But that was inspired by and proved the case for Richard Feynman that gravity waves move through space at the speed of light and have energy. And the last item I want to mention in the history lesson here is what's called the Lambda CDM theory. And this is from the 80s, is a culmination of lots of the information I've presented so far, trying to provide a mathematical explanation of the Big Bang based on these various observations, including the microwave background, ideas of expansion of space. Now, I think it's an odd theory because instead of having space expanding on its own, this is where most of the concept of dark matter comes from, is having some sort of energy or matter in our universe that pushes away all the matter serendipitously at the rates that we observe. But then the lambda, which is the first letter of the theory, is them reassigning a cosmological constant. Now, whether or not it's meant to be the same as Einstein's idea originally, it's the same kind of idea of assigning a kind of an arbitrary pressure to keep the universe expanding, as opposed to keeping it from collapsing. This is an arbitrary pressure to force it to expand at what rates are necessary for the theory. So that's the history portion. Now, I tried to kind of summarize a couple of questions I believe that this history brings up. Is I think there are still persistent issues with characterizing cosmic expansion the way that Hubble presumed, the way that the Lambda CDM theory speaks about, because in kind of a natural system, nothing really is on a line. Lines don't happen on natural systems. You always hear about curves, bell curves, but even Feynman diagrams or whatnot. There's very few linear systems in nature. And even with Hubble and even with the Lambda CDM people, they're always expecting to find a curve somewhere. And so that Hubble redshift is measured to be very linear is kind of odd. That there isn't more obvious a curvature to the acceleration over time. So now also the nature of cosmic expansion, as I mentioned, Hubble assigned it to the fabric of space stretching, so that if it's space itself expands, then there is nothing in the space causing the expansion. It would be something behind the veil, you would say. The veil is expanding. How do you describe that? Or how do you even measure that? But with Lambda CDM theory, it is trying to assign it to a particle pressure, some sort of force or some sort of particle inside the universe. And there always seems to be a kind of a flip-flop between those theories. Even when you try to mix in relativity, the Minkowski space-time continuum that is part of Minkowski theory. How do you have a stretching space, bending space, but mass in the space causing all together causing those different interactions? And it seems like it's a pick and choose of which one you like best for your theory, but I don't think they can't all be true. It really is either one or the other, or something that they're all pointing to that's specific. So I feel like there's a lot of pick and choose there. Also, speaking of dark matter and energy, to date there have been no direct experiments that have proved that it actually exists. All of it is math on paper. None of it is supported by observation, and there's few theorists that actually agree on the mathematical values. So it's one of those items that you'll see front page, top of the screen, what everyone says it is, and it's not everyone. It's the one scientist says it's that. Everyone else is trying to agree that it exists, but they can't all agree what it is. And so therefore having the occasional need for an arbitrary constant it comes back again, because it's kind of trying to fill that gap. So using kind of a similar process to what I was mentioning with my environmental equation, I've been trying to think of trying to look at how to resolve all of these together. So I've created, I call it a theory on that includes just the items here, that we know that the propagation rate of gravity, or the effect of gravity, is the speed of light. LIGO observed it. Feynman predicted it. Einstein characterized it in his own theories. So gravity moves at the speed of light. And then based on the cosmic microwave background, the universe is homogeneous. All the mass is evenly distributed. And it seems like if there was a beginning to the universe, it started that way. And the mass was, and when the universe started, that mass was spread out over a distance that we can't even observe. Hundreds or probably hundreds of trillions of parsecs. And then the very well characterized, highly successful theory of Einstein's general relativity, pretty much Newton's gravity equation 2.0. There is little doubt that it is a highly relevant and effective theory in just about every particle or mass interaction that we can measure. So using only these first principles that few that have any doubt are relevant or accurate is what I've used to try to look at alternatives for how the universe looks the way it does. So when talking about gravitational forces, most people think about something very practical, like standing on Earth. So the Earth holds us down to it, or the moon goes around the Earth. But few people really seem to consider that the objects are kind of orbiting each other. They're impacting each other. We're holding the Earth to us, just like the Earth's holding us down. The moon, the Earth orbits the moon, much like the moon orbits the Earth. There's force in both directions. There's interaction in both directions, which was I wanted to mention the Valentin Zarkova podcast that you did. She discussed that in describing differences in the orbit, differences in the distance between the sun and the Earth for environmental reasons, kind of to refine the Minkowski cycles. And I thought that was brilliant. And I also find it odd that I personally haven't heard that from anyone else. But it is taking that reality that even Isaac Newton realized, and applying it to something more advanced, more refined. So kind of throwing this other picture, not too much of a difference, but instead of looking at just two objects, if we consider a field of objects or a distribution of masses, regardless what they are, all of them are impacting each other in some way. So there is no one object being affected by everything else. It's not everything else is being affected by one object. Everything affects everybody gravitationally, or by time dilation, or whatever energy is being emitted. So there's a total interaction. So looking at that gravitationally, if you had a group of masses, let's looking at the kind of the ball to the far left there. If you had a group of masses that are all equidistantly away from a point in the center, and the density of those masses, the average density of those masses over an area. So let's say maybe like a magic school bus basketball. So let's say you have a basketball that's got a rubber that's a certain thickness, and at the very center point of that basketball, you had a gravity meter, a magic gravity meter. It would show a force of gravity from that rubber skin of a specific level. But if you made a basketball that was just twice as big, but the thickness of that membrane, the thickness of the skin is the same, so the same distribution of mass across that area, the center point would have the exact same gravitational measurement. That force of gravity at the center would be the same. And if you nest those two balls together, the force of gravity at the center would be double. And so on and so forth. So what's interesting is this appears to be kind of a natural condition, but you can see that there's a linearity. To add one, you double; add another, you triple, and there's a linear progression if you nest these spheres, spheres of equal surface density. so looking, so mathematically, at the top left, that's Newton's force of gravity equation. But the area of a sphere is the equation to the right, and I've integrated them. And this is not simplified either. Please, for anyone watching that knows math better than me, which I think is probably most of your watchers, this is not a simplified equation, and I would love to have anyone challenge me or ask me or enhance what I've written here. But as far as I can tell, if you have a continuing progression of these kind of mass spheres, this red line here shows that for any given radius, for any given radius of a sphere, you're going to add the same amount of mass force to the center. It doesn't matter what the size is. If the surface density is the same, it's going to be the same gravitational force at the center. But if you look at the blue line is the absolute mass, the amount of mass at those different sphere diameters. So the amount of mass exponentially increases. It curves up. But because of the area, because the loss of energy over distance is the same as the increase of mass at a distance, that's where it turns into a line of force. So if you add spheres together, and that would be the yellow line, if you add spheres together, compounding them like a Matryoshka doll, it creates a line of force for as many spheres as you add. The amount of force is additive, just directly additive. So I'm going to throw in one other thing. These equations here, I'm showing diameter, and I'm showing force, and I'm showing gravity. But oops. Oh, sorry. Wrong direction. But I'm going to add one more variable, is the speed of light. So the LIGO observations I spoke about earlier from 2017 were based on the theory of gravity moving at the speed of light, and that they would be detectable per Feynman's theories. And so gravity moves at the speed of light. But the cosmic microwave background implies that the mass distribution of the universe at the beginning of the universe was such that when particles started releasing microwave energy, or the photon epoch, basically less than a second after the universe would have begun in Big Bang theory, that over massive billion, trillion parsec distances, that the mass of the universe was evenly spread out. And as I mentioned, so with the Big Bang theory, regardless how the mass got there, regardless what was in the original point in space, time was the beginning of time was less than a second before all that mass is spread out evenly at the distances it was. And that we have an observable limit to the universe, and that we believe that mass exists beyond that observable limit, implies to me that if at the beginning of the universe, the gravity waves or the time dilation caused by those masses beyond our field of vision now have yet to reach us today. So gravitational influence from particles that originated beyond our observable range have not reached us yet. Just like light from stars and galaxies beyond our observable range theoretically have not reached us yet. So I'm bringing up this page again, but replacing radius with time, or effectively treating radius as time being the distance. This theory shows that over time we are gaining the time dilational influence from mass that is beyond the observable universe. And that relation apparently would be on a line. Because even though it's a natural case that the rule of squares power loss is over a distance, it's also a natural case that the surface of a sphere is a squared ratio of mass as you expand. So I believe strongly that I have found a line in a natural system. And so what would that line mean to things like redshift? I think it's interesting that Einstein was so quick to accept Hubble's explanation for cosmic redshift being the acceleration of galaxies away from our point in space, because Einstein himself even characterized what's called the equivalence principle, that anything that you could explain through Doppler effect, you could also explain through change in gravitation or gravitational potential. And so if you see an object that seems red in space, it could be moving away, but it could also be in a different gravitational potential space than you are. And both of those are true. They're both absolutely true, and they're both absolutely applicable. But when we're talking about seeing a galaxy at 20 parsecs and thinking that the color is a little bit off, there is more than one possible explanation. And so in this theory, if all the masses in the universe, if we assume that they're just standing still, but we're getting more time dilation from a further and further distance, if you have electromagnetic signal, light, coming from a star at a great distance of tens of parsecs, by the time it reaches our point in space to observe it, the gravitational potential will have shrunk between when it was sent and when it reached our point in space. And that would be an absolutely equivalent answer to expanding space. Space wouldn't necessarily have to move if our gravitational potential is shifting. And having an explanation for that would actually revise that theory entirely. Now, I do want to throw in a little bit more resolution is even though that ratio with gravitational potential appears to be linear from that equation, time dilation, why time dilation was hard to characterize or was kind of hidden until the Mercury problem, is because that isn't a linear situation. That is actually it's not even logarithmic. It's a hyperbolic relationship where at low rates you see almost no difference. So you have to have a relatively large influence to be able to have a measurable effect or an obvious effect that you can't explain any other way. To give you an example, the fastest objects that we can produce at all with rail guns and other except for particles, individual particles in the particle accelerator, we can get close to the speed of light. But any mass, any of a molecule, relatively large molecules, the fastest we've been able to accelerate them is less than 0.1 times the speed of light. Or if you're talking about an extreme cosmic environment, like, for example, the neutron stars that collided to make the gravity waves that we observed, they spin at an incredibly high rate and they have a huge amount of mass, but they still only reach the velocities that happen on neutron stars, even in collision. They still only reach about a quarter of the speed of light. And so these are incredibly high density, incredibly high velocity scenarios that we think are so extreme that it defies imagination. And we're most of them don't even get a quarter of the way up the scale of time dilation. It's almost seems like it's practically in the noise region of that. It's a refinement, not necessarily defining it. So for example, if you have a kid in school, they're going to use Newtonian math for the most part. You're not going to usually get to time dilation relativity until maybe college or maybe even graduate school. because it has a limited practical application at the speed of life. But over time, or when you're trying to look at very fine elements or very small details, time dilation will have an effect, and it will have a slightly curved effect as well. So let's see. So time dilation, two ways to describe time dilation would be that it is really just the difference in speed between particles in any two places. If you have a place that has more time dilation or more gravity present, those particles are going to move at a rate at a speed slightly different than those with less gravity or with less time dilation. So satellites in orbit, to give an example, is GPS satellites in orbit. They tend to gain, I believe, 17 milliseconds a day, which for a GPS satellite is massive because they're measuring distances that they need to be accurate at distances over hundreds or thousands of miles. So that small difference is problematic. So they need to actually have their clocks running at a slightly different speed to compensate for the time dilation, allowing their particles to move too fast compared to clocks that would be on the surface of the Earth. So it's a constant reminder. Your GPS on your phone is a constant reminder that time dilation does in fact happen. And so that is a measurement that's so small and detailed, it needs the precision that time dilation would impact. So as far as redshift goes, as far as those theories go, I believe that both time dilation and gravitational potential will have an effect on redshift. But time dilation is interesting because since we measure distance by how fast particles move, time dilation is technically a way that you could consider space stretching. So where Hubble says space is accelerating quickly to explain all redshift, I would agree in a manner of speaking that time is stretching, but very slowly for the effect of time dilation, depending on how you'd like to measure it. Now, coming back to the cosmological constant, Einstein had the idea that we needed a cosmological constant to have a continuing outward pressure to keep the universe from collapsing. And Hubble needs the universe to expand to explain redshift. So they kind of canceled each other out or complemented each other. But with the Lambda CDM theory, trying to explain how dark matter pushes the universe apart, they've reintroduced the idea of a cosmological constant as being the value of dark energy or dark matter force. Now, I'm going to run through a couple of values here. The current observed value is in the middle of the screen here. It's 1.1 times 10 to the minus 52 meters minus cubed. It's a natural value. Now, I've taken my concept of outward pressure or a slight expansion of the universe being based on time dilation, and just trying to convert redshift directly into time dilation. No other considerations being made. I come up with a value of roughly 4.12 times 10 to the minus 39. And I'm sure that's not really even the best value. And as I mentioned before, I think there's a combination of time dilation and gravitational potential involved. So it's kind of a split between the two. But at least I'm still somewhere in the negative powers. But Lambda CDM, with all the math that they have and with all the theories that they're working with, and with 40 years of research, their calculated value is 1.1 times 10 to the 68th power, which is a positive value, which is 120 power away from the observed value that they believe is accurate. So since their observed value is not even in the ballpark of their calculated value or predicted value, I would say just on that standard alone, I think I might have a better idea of where the observed value is coming from, or I have a theory that I think is worth looking into to explain why what we consider the cosmological constant pressure to be coming from. But do I think anything I've said here is the answer? I think the correct answer in all cases is I don't know, but science is never settled. Frankly, settled is probably the least scientific word in the dictionary, at least the way it's used these days, because falsifiability and scalability are the key. You have I believe that theory has to apply in all spaces, all scales, but it also needs to be provable. It needs to be falsifiable, unlike dark matter, which for 40 years has been wholly unprovable. Maybe that needs to stop or be redirected. So if there's an exception to a theory, if there's observations that don't line up, it probably means the theory is not complete or is not true. And I think what I call my dilation flooding theory, I think has very wide compatibility. I'm actually struggling to find scenarios that it doesn't seem to apply to observation. But you have to have methods to validate it. So through either mathematic modeling based on existing functional theory has to match up, kind of like Einstein's models fit with Newton's. It just enhanced it, expanded the field. So for example, for the model that I'm proposing, I think that if it's found to be accurate, it'd be a great way to figure out what the standard model particle density of the universe is. So you have the cosmic microwave background, but you're only really observing one particle. And then how we observe other galaxies, there's only the luminous particles that we observe there. There's so much dark matter or dark unilluminated matter, so much matter and gas that we don't necessarily identify and might not properly consider, that having an idea of how dense the universe is supposed to be might actually help us enhance our observations in those cases. My idea that time dilation is the cosmological constant, is the outward pressure that we can assign to observations in the universe, consolidates it down to 100-year-old Einstein relativity. But I can't think of a reason why that wouldn't be the case. I'd like to see that proven wrong. And so having this revised expansion model of the universe, I think, would be a way of helping address a lot of issues with getting into quantum mechanics, which is kind of out of the ballpark for today's conversation. So how, and coming back to the environmental aspect of this, I think all disciplines, no matter what they are, there is a resistance to independent thinking, and that's natural because people want to get into their groove. They want to have their ideas and feel as though they're successful. The only problem is in science, everything needs to be challenged and doubted, and we have to have the bravery and wisdom to admit that we're wrong or another idea is more correct. We're never going to find all the answers, partly because we're in the experiment. We're in the petri dish. We don't necessarily know what the countertop looks like. We're never going to know what's under the table of the experiment of the universe. We're still trying to figure out where the edges of the petri dish are. So we have to have that kind of wisdom and humility to realize our limits and be open to entertaining any idea. But now there's also, of course, that's philosophical. There's also financial incentives to kind of stick in your way. I mentioned dark matter specifically. And it seems like roughly $500 million is spent directly towards dark matter research one way or another. I believe there has been at least one or two satellites launched with that purpose in mind, specifically, to no avail. There's no observations that were made that were of any benefit. And then there's the what I like to call the kind of the Star Trek effect as well. People like to believe certain things or get excited about certain ideas, or whether it's fact or fiction, they don't necessarily want to challenge their worldview. So Star Trek in particular, for anyone watching, I love the first series. Grew up with the Next Generation, but it was designed as fiction to discuss philosophy. So even Gene Roddenberry didn't believe that many of the science aspects were true. They were believable ideas to drive the narrative. And but then even with Einstein, he believed in a finite universe, and even at one point mentioned how he would never entertain a theory of he believed in an infinite universe and never would entertain the idea of a finite universe, of a time limited universe. And then his mathematics was highly deterministic, showing distinct patterns or showing knowable solutions with relativity and quantum mechanics. The first lesson with quantum mechanics is you can't know the answer. It's statistical, non-determinate, and he was highly resistant to that. So resistant, he actually came up with argumentative equations to debate it, and those equations were so effective at describing quantum mechanics. We still use a version of the Einstein equations today, even though they were meant to argue against quantum mechanics. It's a very interesting kind of a scenario there. And I find that for people that want to share new ideas, there is a very high threshold for participation. I have to admit, I'm probably the cause of some of that issue, because there is a very saturated market of outlandish ideas, and lots of people are really into their outlandish ideas. So it is understandable that being open to everybody's ideas all the time can be overwhelming or largely pointless. But they're not all going to be losers. There's going to be some ideas that do make sense, or there'll be ideas that will drive you to other ideas. Some of the theories that I have, some of the hypotheses I've been making, are based on, frankly, dumb ideas or philosophical ideas that didn't seem to make any sense, but it made me look at the box from a different angle, made me consider something that I didn't before, and it ultimately had me enhance what I was considering. And then lastly, there's often seems to be a cost of entry for professional exposure. Partly, I'm sure, to weed out outlandish ideas, but it seems like lots of the people invested have either put so much into it themselves that they don't want to see any cracks in the facade. But then it makes it difficult for anyone that has a legitimate idea to get any attention in the market these days. And that brings me to the end of my rant. I want to thank you, Tom, and I welcome anyone to email me at the email address I have here, or find me any other way on X or any social medias I'm participating in.
Do you plan to look at the comments at all on YouTube in case people do have questions out there?
Oh, absolutely. I've participated in a few YouTube videos, not directly related to these topics, but I do find myself going through the comments and responding to anything directly. However, I would like to say that I don't think YouTube comments is necessarily the best way to communicate. For little blurbs here and there, I'm suspicious of it filtering out some of my comments that I can't figure out why it would filter out. So I'm not trying to say I'm suspicious of Google or YouTube as a whole, but I do think that the best way to communicate, at least to to any strong degree would be by email. I'm actually planning on trying to be much more active on my X account as well. But yeah, I would say by email or X would probably be the best way to comment. But I'll be trolling your comments list for sure on YouTube.
And then in the show description, I already have links to your X account and to your website, so people can find you over there. Would you like to talk about your environmental journey at all?
Yeah, so I think I find, as I mentioned, I've always been very logical. I try to consider things from a mathematical perspective, having been in engineering and design for a while. But I think it's interesting the tidbits that have popped up from time to time. So I remember being at work 20 years ago, and frankly, I was using the bathroom, wanted something to read, and the guys I worked with were into cars, classic cars. And in a classic car magazine, there was a whole article about how the government was looking into legislation to regulate carbon dioxide, and how they were even already saying this seemed bizarre. Why would they do that? And as car enthusiasts, they were all concerned about what that would mean for them regulation wise. It wasn't and about maybe a year after that, I was at a NASA facility talking to a project director and a project manager, and he took me out to lunch and was mentioning how NASA was tasked with looking at man-made global warming, man-made environmental changes, and how NASA just kind of whole-handedly decided that there was really no validity to it. And I think he even mentioned the Minkowski cycles for. Am I saying that one right? I think
Milankovitch, is that the one? Milankovitch?
Yeah, Milankovitch. Sorry, yeah. But the Milankovitch cycles for being the best explanation for most variances that we see in history. But then it was a couple years later that Al Gore had his movie, and I actually really appreciated the global warming swindle film, because not only did I already know that the Al Gore film was garbage, it was interesting to see from the scientist who developed the research that Al Gore lied about directly. He mentioned that, oh no, he lied about what my charts say. And there was one chart in Al Gore's whole presentation, and it was a lie. But it doesn't, but none of that means that I don't think that stewardship, efficiency are important things. So I have always been interested in efficiency, but also being forward thinking in materials. So I have an older home, not necessarily old. I'm from the East, so old is hundreds of years old. Now I live in the West, so old means a couple of decades. But my house is from the 60s and had wood shake up until I recently replaced it. And but I had been keeping my eye out for what Elon Musk had been working on, because for over a decade he was talking about making roofs. So I actually ended up purchasing the Tesla solar roof, which if you don't mind, I could show you just a couple slides of that.
Yeah, let's do it.
So here it is, my old shake roof, nice and raggedy, but that roof is 60 years old, and they stripped it down to the deck, replaced it. You got the underlay, and there you go. They built up a roof. And why I was excited about this was for several reasons. I really needed a roof. So we have solar people come by, try to solicit solar panels, and I pointed out to them. But I always tell everyone I actually really just needed a roof, and it fit my situation of I have an HOA that requires certain materials, but my house is designed with shake, so it can't handle a heavy material. So the nexus of materials and weights and honestly being an honest person and doing above board work, it actually ended up costing about as much as it would have for me to have gone with a traditional roof in my permitted materials. But it also includes solar, and it's very durable. And so I was very excited about that. And even though there's all this absolutely bizarre green space replacement going on right now with solar panels and wind farms, which is mind-boggling because they're not that efficient, and chemically they're not beneficial in the grand scheme of things. For roof space, if you can provide a material that makes your house more durable and more energy efficient, then I think that's great. It's honestly, my roof is wasted space, and I wanted something better than a crappy soft tile up there. I wanted something that would last. And so I am a big proponent for it, and it's actually a real interesting thing. But I do agree that lots of what's been going on with solar panels has been not beneficial, or lots of the legislations, lots of the regulations has really been pushing things that haven't been a benefit. So I do think reusing used space is great, especially if it's cost efficient, especially if it makes sense. And in this case, it's a cost saver for me. I could show it that it works out for me. But for most people, it's a big upfront investment with little payoff, or you're expected to sacrifice the stability of your home. And it really has to be something that makes sense. Bottom line for you, efficiency for yourself and for your area. And well, I guess that's that.
So I'm curious, were there subsidies or credits or something that you got for installing it? And also, do you get some sort of credits for producing solar power and putting it on the grid?
At the time, there were some tax credits. Honestly, not they were sizable, but not game changer. It was just kind of icing on the cake. Again, like I mentioned, because of the types of materials that were available to me, it ended up just kind of being a wash. Actually, with the subsidies, I think it actually ended up being slightly cheaper. Tax credits. But what was the other part of your question?
Oh, I don't know. I just was curious about the solar power that's produced. Can you keep track of how much is produced, and are you getting subsidized for that?
I can. It's very well tracked. It's all electronically tracked with the electric company, and I do benefit from that, especially in Southern California. It's like in my equation, they're trying to make electricity so costly you have no choice. And they're even regulating it that new homes must have some solar panels on them, no matter what. But then they get rid of all of the other sources of power. So California is in a situation that when the sun is down, we buy everything from Nevada, or it seems that way. I can appreciate the distributed generation during the day. I think that's a neat idea. I don't know if it should be forced regulated. I think is a good idea. But at nighttime, if you're buying everything from another state and you have all those line losses and they're just producing at a different set of regulations, then what's the point? So I'd rather have less windmills out by Palm Springs, less solar farms out in the middle of the natural desert, and they should start up a couple of nuclear plants and be done with it. Instead of decommissioning them. We've recently decommissioned one from near San Diego, which is frustrating.
I am curious. I don't know if you've had the solar panels long enough, or the solar roof, to figure out if they get dirty, or you're supposed to hose them off. Does that make any difference? Or
actually, they're very dirty right now. I don't know if I can see if it's making a power difference. I just washed one side. So for power generation, you are supposed to try and keep them clean. Online, I bought an extended. It's a brush with a water thing that's designed for cleaning solar panels, and I use that to brush off the roof. You can walk on this roof, so if I was more brave, I could just go up there and clean it by hand. but I don't want to walk on it. You can. It is very durable, but yeah, I wash it off from time to time. Like I said, I'm not sure. I'm sure it does make a difference in the power generation, but because I was primarily interested in a durable, modern roof, the power generation does make a difference. I do save money compared on the utilities there, but that's actually I like to mention to people that is actually a secondary consideration for me. That's not the reason I got it to begin with. But yeah, I'm not sure if you can see here. There's the value here that is about maybe 5 kilowatt production a couple days ago. And I didn't clean the whole thing, but I did clean most of it last night. And it looks like maybe I'm bumping up. It could be the weather, but it's bumping up maybe another half kilowatt hour during the midday. So
okay, very interesting.
It'll help. It does help a little.
Now my last question is, I'm going to put up a link to this Jubilee video that you sent me where they were trying to pick out the flat earther. I thought the whole thing was super interesting. Do you want to comment on that and comment on the fact that the young folks think that they understand climate better than the old folks? What was the deal with that?
No, that's a interesting one that I've gone through a lot of the comments on. And for anyone who watches it, it is a very very silly game. But yeah, there for the people that participated, a lot of them are younger. Though I mean, they are quite well educated. Lots of them are even in their master's studies. So it's not a matter of textbook education. But when it came to questions on political leanings or environment, there's a lockstep mentality of and I think it's bizarre. If you are conservative thinking, then you can't be that smart or educated, or if you don't, or it's obvious that the world's dying from global warming and it's just what are we going to do to solve it before we all die a horrible death? And that was all of them, every one of them. And that was younger than 30. As far as, yeah, I don't know how old everyone was, but I think just about everyone else was under 30 at the time. And it was kind of bizarre that it was a lockstep requirement and also completely off topic from the game.
Okay, very good. Yeah, the whole air of smugness really got to me there, but that was not too long ago. Was that a year or two ago? Or
that was a year ago. Yeah. Okay. And I've actually yesterday I just recorded another video with that group, so it's kind of a fun activity. But they are very entertainment driven videos.
Okay, so yeah, thank you very much for doing this. You're a very interesting guy. I hope people go to your website and watch this video as well. Any other points you'd like to make before we finish off here?
Oh no, I think it's good. Okay. I mean, like I said before, I've always got something I'll answer anything, but I got to stop sometime.
All right. Thank you very much for doing this. We'll talk to you next time, George Woolridge. Goodbye.
Thank you.